Welcome to this third video about the preparation of alkynes. This video is about the arylation of terminal alkynes at the acetylenic CH bond. These reactions are easy and inexpensive to perform, and the products can be transformed into many other types of compound. Alkyne arylation is therefore a versatile and valuable strategy for the assembly of larger carbon frameworks. There are two main strategies to arylate terminal alkynes with aryl halides or other aromatic electrophiles: aromatic nucleophilic substitution and transition metal catalyzed arylations. You can find a more detailed discussion of uncatalyzed aromatic substitutions in my videos about the preparation of aryl amines. These proceed as sketched here, by an addition-elimination mechanism. Particularly good leaving groups are fluoride and nitride. Most transition metal catalyzed alkyne arylations are mechanistically related to the Sonogashira reaction, where both a palladium and a copper catalyst are used. Arylations with nickel, palladium or copper alone are also known. In the Sonogashira variant, an aryl palladium intermediate reacts with a copper alkenyl complex to yield an aryl alkenyl palladium complex. Reductive elimination regenerates the catalyst and yields an arylated alkyne, as sketched here. To avoid protonation of the copper acetylide or the palladium complexes, these reactions require a weak base, such as an amine or carbonate. Particularly good leaving groups at the arene are iodide and bromide. Aryl fluorides do not usually react this way. Let's check some specific examples, starting with arylations by aryl fluorides. Here, a rather weird mixture of sodium, calcium hydroxide and a Grignard reagent was used to arylate an alkyne with an aryl fluoride. Generally, it isn't a good idea to mix alkynes with sodium or metallic zinc, because these metals can reduce alkynes to olefins. Anyway, this did not happen here, and a high yield of diaryl alkyne resulted. This here is a rare example of palladium-catalyzed alkyne arylation with an aryl fluoride. Despite the excess of alkyne and the high reaction temperature, only one of the two fluorine atoms was displaced. In addition to the palladium-0 complex, two equivalents of a strong base were required. Aryl chlorides are often unreactive and require electron-rich, sterically demanding palladium complexes to undergo palladation. Here, such a reaction was conducted in the presence of water with tetramethylguanidine as base. The target product was obtained in excellent yield. In this example, phenylacetylene was generated from its addition product to acetone and then coupled with a 3-chlorothiophene. Potassium carbonate was the base and the reaction was run in acetonitrile. This is a particularly convenient solvent for such reactions because many palladium salts are soluble in acetonitrile. Aryl bromides are more expensive than chlorides but also more reactive. Many examples of copper-catalyzed nucleophilic aromatic substitutions with aryl bromides have been reported. Also, alkynes can be arylated this way, without any palladium, as shown here. With most aryl chlorides, however, copper catalysis alone did not give high yields, like in the second equation. Only reactive aryl chlorides, as the one of the last equation, underwent a high-yielding alkynylation with copper catalysis alone. This is another example of alkyne arylation without any palladium complex. Only 3% of copper catalyst was required, and bromide was displaced selectively. This here is an attempt to arylate unprotected acetylene with an aryl bromide under typical Sonogashira conditions. Acetylene was generated from calcium carbide directly in the reaction mixture, in the presence of both palladium and copper complexes. A mixture of monoarylated and diarylated acetylene resulted. A better strategy is the use of some synthetic equivalent of acetylene, for instance 2-methylbutanol. Sonogashira coupling with an aryl bromide followed by base-induced dealkylation of the propylylic alcohol yielded the monoarylated acetylene. Sonogashira and related couplings often proceed very cleanly. Here, hexabromobenzene gave 64% of the expected substitution product and only 10% of a reduced byproduct. This is an excellent result for a 6-fold aromatic substitution. With other nucleophiles, more complex product mixtures would usually be formed. Still more reactive than bromides are iodides. Here, phenylacetylene was arylated with an aryl iodide and 2% of palladium acetate, without copper or any phosphine ligand. The reaction already proceeded at room temperature and in the presence of air. When copper was added, though, mostly a Glaser coupling of the alkyne occurred. Thus, for arylations of terminal alkynes in the presence of air or other oxidants, copper complexes should better be avoided. This is an optimized Sonogashira coupling of an aryl iodide. The base was aqueous ammonia and the reaction was conducted in NMP at 40 degrees Celsius. Phenol-derived aromatic electrophiles, such as sulfonates, esters or carbamates, are about as unreactive as aryl chlorides. Alkynylation of such substrates requires sterically demanding catalysts and often a high temperature. In this example, an aryl carbamate was coupled with silylated acetylene with the aid of 5% of a rhodium carbene complex. The alkyne was generated by base-induced dealkylation of a propargylic alcohol. Mesylates are easier to prepare and less expensive than triflates or tosylates, but can be cleaved into phenols and a sulfene by strong bases. Here, with 2% of a bulky palladium complex and potassium phosphate as base, hexyne was arylated successfully with an aryl mesylate. Nitro groups can be displaced by nucleophiles both in uncatalyzed and in palladium-catalyzed aromatic nucleophilic substitutions. Interestingly, in this example, a nitro group was substituted faster than fluoride from 4-fluoronitrobenzene. Although elemental nitrogen is among the best leaving groups known, aromatic diazonium salts are also strong oxidants. Moreover, nucleophiles readily add to the terminal nitrogen atom under neutral or alkaline conditions, yielding azo compounds. Nevertheless, under optimized and acidic conditions, alkynes can be arylated with diazonium salts, as in this example. Here, phenyldiazonium acetate was generated in situ from aniline and tertsbutyl nitride. Few examples have been reported of the use of quaternized anilines as electrophiles. These reagents are not easy to prepare and may also react as methylating reagent. Here, an alkyne was successfully arylated with such an ammonium salt and 10% of a bulky palladium carbene complex. This is an example of Sonogashira reaction with a heteroaromatic thioether. The electrophile was a hardly aromatic but strongly electrophilic pyrazinone. Interestingly, thiophenol was displaced faster than chloride and no poisoning of the catalyst by the thiol occurred. Also, aromatic sulfoxides can act as electrophilic arylating reagents for terminal alkynes. Both a strong base and a bulky palladium carbene complex were used in this example to bring about the arylation. The primary alkyl chloride remained unchanged. Arene sulfonyl hydroxides are a rather peculiar type of electrophilic arylating reagent. In the presence of a large excess of copper acetate and a palladium catalyst, these can also be used to arylate alkynes, as in this example. Polyhaloarenes are acidic and can sometimes be deprotonated by lithium or sodium alkoxides. Here, lithiated pentafluorobenzene was coupled oxidatively with a terminal alkyne. The reaction was catalyzed by 10% of a copper complex. Benzoyl chlorides or otherwise activated benzoic acids undergo palladium-catalyzed decarbonylation when heated strongly. Aryl palladium complexes are formed as intermediates which may undergo C-C bond formation with terminal alkynes, as in this example. Pyridine N-oxides can react with nucleophiles in position 2, in particular if the N-oxide is activated by alkylation, acylation or sulfonylation at oxygen. Here, no such activation was necessary, but the alkynylation only worked with a highly reactive isoquinoline N-oxide, not with pyridine N-oxides. Desilylation with TBAF gave a diarylated acetylene. Metallated alkynes can also be generated by treatment of vinyl halides with strong bases and then be arylated directly. Here, for instance, a vinylidene dibromide was first heated with an excess of cesium carbonate in DMSO for 15 hours and then coupled with an aryl bromide in the presence of 5% of a palladium catalyst. A high yield of diaryl alkyne resulted. When alene is treated with 2 equivalents of butyl lithium, dilithiated propene is obtained. Such dimetallated alkynes usually react with electrophiles first at the propagyllic position, but the product can isomerize when treated with bases. In this example, the dianion was arylated with an aryl iodide in the presence of copper and palladium, and a conjugated aryl alkyne resulted in high yield. Let's check some potential side reactions. As described in the next video of this playlist, terminal alkynes readily undergo transition metal catalyzed oxidative or non-oxidative dimerization. Then, because of their electrophilicity, alkynes tend to react with nucleophiles. Strong bases can isomerize alkynes to allenes, 1,3-dienes, or other alkynes. And during aromatic nucleophilic substitutions, reduction of the electrophile is another common side reaction. This here is an example of alkyne arylation with an aryl bromide where the initially formed product cyclized to an indolone. Even simple 2-alkenyl phenols can cyclize to benzofuranes under mild conditions, as in this example, without any strong base. Byproducts of this specific example were the reduced aryl iodide and a product where propene had reacted with the first intermediate. Sometimes such cyclizations can be prevented with a less polar solvent. Many reactions are slower in non-polar solvents like toluene or cyclohexane, and higher selectivities may be achievable in such solvents. Here are some further examples which you can also find in the description of this video. Under the Community tab of my channel, you'll find a PDF version of the slides. The next video of this playlist is about the vinylation and alkynylation of terminal alkynes for the preparation of enynes and dienes. So long!